Here we go. This is the slide I wanted to start on. So in this recording, we're going to focus on filtration within the kidneys, within the nephron specifically, in more detail. We need some pressure to help power filtration. And this filtration pressure is going to depend on two key things: hydrostatic pressure and osmotic pressure. As we look at hydrostatic pressure, we have two different hydrostatic pressures. Hydrostatic pressure within the blood and hydrostatic pressure within the capsular space. In the diagram I have here, capsular hydrostatic pressure is represented by the green arrows, and blood hydrostatic pressure is represented by the, we'll say, the blue arrow, though it looks kind of purple to me right now as I'm looking at it. So blood hydrostatic pressure pushes liquid into the capsular space. And then capsular hydrostatic pressure is going to push fluid back into the bloodstream. And what we find is that the blood hydrostatic pressure is about 60 millimeters of mercury, whereas we have 18 millimeters of mercury for the capsular hydrostatic pressure. In other words, there's more pressure pushing blood or filtrate out of the bloodstream as opposed to pulling that filtrate back into the bloodstream. And the key reason for this is because our afferent arteriole will always have a wider diameter. Excuse me, the afferent, A for axis, the afferent arteriole always has a wider diameter than the efferent arteriole. That efferent arteriole is smaller and can't transport as much liquid at the same pressure compared to the afferent arteriole. So we'll have more blood entering the glomerulus than exiting the glomerulus. And the difference in volume is equal to the volume of filtrate produced. We're also going to have osmotic pressure. Osmotic pressures typically pull. So to review, with hydrostatic pressures push, osmotic pressures pull. And we have osmotic pressure in the bloodstream. The colloid osmotic pressure of the bloodstream is all dependent upon blood protein concentrations. So the COP, colloid osmotic pressure, is based on the amount primarily of albumin in the bloodstream, and that's about 32 millimeters of mercury. The glomerular filtrate has almost no protein, so it effectively doesn't have any colloid osmotic pressure in it. So what we find is that we have colloid osmotic pressure in the bloodstream pulling fluid back into the bloodstream, and then the blood hydrostatic pressure pushes fluid out of the bloodstream into the filtrate. And the capsular hydrostatic pressure is going to push fluid back into the blood. So these are the three forces that we typically are going to look at that give us our filtration pressures. And we can total them up or sum them. So we have positive 60, minus 32, minus 18, giving us a net filtration pressure of approximately 10 millimeters of mercury out of the glomerulus into the renal tubules. So this is what causes the net movement of filtrate from the glomerulus, from the renal corpuscle into the renal tubules. If our blood pressure is too high in the glomerular capillaries, that could cause the glomerular capillaries to rupture. And as they rupture, they'll eventually heal and have lots of scar tissue form. And glomerular capillaries filled with scar tissue are no longer highly functional. They become much more rigid. And we have nephrosclerosis take place, where we have a thickening and a reduction of flexibility of those renal blood vessels. And this nephrosclerosis ultimately leads to kidney failure or renal failure. It's sometimes referred to as. As we look at the glomerular filtration rate, our glomerular filtration rate is the amount of filtrate we make per minute by both kidneys combined. So we take the glomerular filtration rate, which is the overall amount of filtration that we do in our blood. And to do that, we take our net filtration pressure of our kidneys, we multiply it by a filtration coefficient. And this fudge factor, this K sub F, is going to depend upon a lot of different things. It depends on our age, our overall health, our biological sex. These are things that are important for determining our overall filtration rate. Generally speaking, Males have larger kidneys and have a higher overall filtration rate because they have a higher overall surface area of their filtration membranes compared to females who typically will have smaller kidneys and less overall surface area of the glomeruli of their nephrons. So for a male, a typical, we'll say just an average, quote unquote, average healthy male, we produce about 125 milliliters of filtrate per minute, or approximately 100 liters a day of filtrate. This corresponds to about, and this is very rough conversion. If I had to convert that into gallons, that would be about 34-ish gallons. Whereas this 150 liters a day of filtrate for a female, if I divide that by 4, 150 divided by 4 gives us about, we'll say 38 gallons a day of filtrate per female. So 180 divided by 4, we'll say about 48 gallons a day of filtrate for an average adult male. And that's pretty sloppy conversion. I didn't use a calculator at all for that. So as we're looking at this, in other words, we just make gallons and gallons and gallons of filtrate every single day. So as we're looking at all this filtrate that we make, there's no way we can urinate that all out. It's about 50 to 60 times our overall blood volume that we produce in filtrate. And so we have to take all of that filtrate we make and we have to reabsorb the overwhelming majority of it. 99% of our filtrate is reabsorbed because we need to pull that water back into our bloodstream. And we are left with about 1 to 2 liters, about a quarter to a half a gallon of urine per day. That's all we have for this recording. If you have any questions or comments, please feel free to post them in the class discussion boards or to shoot me an email. And as always, happy studies.